Invited plenary speaker, Dr. Douglas Bates. Thank you both.
Thank you. So I'll be very brief. I'll just give a very brief introduction since Professor Bates will go over his background, but he's a very prolific researcher with hundreds of thousands of citations throughout his career, as well as an impact to a broad audience through his contributions in open source and civil computing with vast experience that we can all profit. So we're a very short introduction.
How does that look? Have we got it?
Doesn't seem so. So what I'll do is I'll share the slides and you just let me know when to click.
Okay. All right. Well, yes, I want to talk about the strange trip that we've been on. So if you could go to the second slide, please. Okay. Yeah, some of you might know from the Grateful Dead song Truckin', they have a refrain about what a long, strange trip it's been. And indeed, the history of, first of all, S and then R has been a long and very strange trip. Next slide, please. So it's amazing to look back on the development of the tools. I will emphasize that it wasn't always clear that this path would have been successful. And it has been, which is just unbelievably fortunate for us. I will tell you that one of the first meetings, we'd been working on the project for about a year before we ever got together. And the core developers were strewn all over the globe. And the first time that we got together, Rossi Haka said that they felt that if they had a couple hundred people using R when they were first developing it, they would have been a success. And there's certainly more than that. So what I want to talk about is the development of S in the 1980s and R in the 1990s, and try to put all of these developments into some context about what was happening in the world of computing. My slides have a lot of links to Wikipedia. So it's an interesting way to create a presentation is just sitting around browsing Wikipedia. I was going from my own memory, but of course for dates and references and so forth, it's much better to get to a more authoritative source. And Wikipedia is generally a good source on technical topics. Next slide, please. So I started computing in the 1960s, but I didn't really do too much development until the 1970s when I was working on thesis research. And that I was doing not in what was done at the time, the typical writing some Fortran code. I was actually working on an algo language, which was interesting given some of the later developments. I first heard John Chambers talking about S in the late 1970s, and I'd been aware of the Unix projects at Bell Labs. So I had the great good fortune to work with John. I was at Bell Labs on sabbatical in 1985, I think. And then in the 1990s, R came along. And as John has said, it changed everything. So I have been a member of R Core since 1997. I'm not sure if you can see that. Well, we'll go back to that later on. I'm no longer active in the development of R. So the fact that I'm still listed in the listing of R Core is more a courtesy because, as you see at the last bullet item on this slide, I've predominantly been working in Julia for the last decade. Anyway, I know base R pretty well, and I have some experience with Python from the 1990s and early 2000s for website development. Next slide, please. So the very early days of computing. the hardware of the 1960s and the 1970s was predominantly mainframe computers, and they occupied entire rooms. A university at that time might have a single computer. Often it was an IBM System 360. The 360 was to indicate that it was an all-round computer, which gave them some troubles when they wanted to come out with the next generation. So they just called it 370. They sort of gave up on the full circle. The point here, and these links, you can click on it and see the Wikipedia pages and get an idea of what these things looked like. If you look at the one for the System 360, you'll see that the minimum amount of memory was 8 kilobytes, and the maximum was 9 megabytes. Permanent data storage was limited to 9-track tape. I mean, disk space was just so expensive that it was only for the operating system. So when you were working on the tape, when you were working on your data, that was always stored on a 9-track tape. And the point of that is it could only be, you can only reasonably do sequential processing. You can't do random access. So that had a great influence upon the ways that people used the statistical software. And in fact, at most universities, the biggest use was on batch-oriented statistical software. One of the first was BMDP from 1965. SPSS was introduced in 1968. These are the first dates that they were available, so they are not necessarily the time when they became very popular and widely used. That would have been after. SAS from 1972. Next slide, please. Okay, there's a big discussion going on about back in the day, I had to walk through the snow to the school uphill both ways. Anyway, the hardware came with the operating system and compilers, and there's a little historical fact in here. It started off with COBOL, Common Business-Oriented Language for Commercial Applications, and Fortran for Scientific Computing. So Fortran was a condensation of formula translation. IBM had created this language called PL1, and they pushed it very, very hard. So if you go back and you look at things that IBM was distributing in the late 1960s, early 70s, they were saying, yeah, there's many languages, but soon there will only be PL1. And the initial versions of SAS were written in PL1 and Fortran and some IBM assembler. And it was the failure of PL1 to take off, to become popular, was so acute that in 1985, SAS Institute rewrote the whole system in C so that it could be ported to microcomputers. They tried to get people to create a PL1 compiler for DOS, and they couldn't. So next slide, please. And that meant that the statistical processing tended to be acting like a filter. You would bring in records, you would write out records. The random access memory was very limited, and therefore that would influence the algorithm choices. So there was some discussion a few minutes ago about why SAS can be slow on certain tasks relative to R, and people were saying, well, it depends upon whether it's on solid state drives or disks with platters, hard drives, and so forth. No, the memory access in those days was so limited that you really had to be very, very careful about how you were processing these records. And that's why you have things like early on, you could get a mean of a variable, but getting the median was very difficult because you have to at least partially sort the data to get the median. Minitab was an exception, but it was it wasn't covering the range of analyses that you could get from SAS or SPSS or something like that. Next slide, please. While this was all going on, there was work at Bell Labs, and I think that many of the dramatic changes in the computing environments from the 1970s directly came out of Bell Labs. And there was the Unix operating system, which internally was available in 1971. Externally got around in 1973. Similarly, they created the C programming language. They created the C++ programming language at Bell Labs. And there was this language S for statistical computing and graphics. And I don't know if I'm showing up in the corner here, but this was the initial book describing S coming out of Bell Labs. And next slide, please. The philosophy was centered around software tools, and in the operating system, one would do a lot of piping. So the philosophy from Brian Kernighan and his co-authors was you do one thing and you do it well. And they would, and that was emphasized in S. So the original versions of S followed this philosophy because they were expressed as functions. And so you could take the value of one function and feed it into as an argument to another function. And so it's even more general than pipelines. But what was done there was to create the glue language using RAT4 and M4. So RAT4 was a rational Fortran, M4 gathering these languages together. So there was another book. I'm not sure. Can somebody tell me, does this show up when I hold up these books in front of me?
I'm able to see some books. Yes, thank you, Doug.
Okay. Yes, we see it.
Yeah. So this book was a very thin book on how to extend the S system. It was very interesting because you'd have to get in there and write all this glue code and so forth, and you had all those values sitting in the background. Next slide, please. So in the mid-1980s, John Chambers created a new language, which at that time was called QPE, with representations for both the code and the data. And this became called, this was eventually called the new S language, and it's because there was already an S language. And while that was going on, there was a project to create some statistical modeling software. And so this was, that was known as the blue book, and this was known as the white book. And this was where the classes and methods were first introduced. And it has all of the, this was what the LM function did, this was what the GLM function did, this was et cetera, going through all of these different modeling strategies. And it was also trying to create a homogeneous set of modeling functions that could respond to methods. So, print.glm or plot.glm might be different than print.lm or plot.lm, but you did have the ability to think of them as acting in the same way. Next slide, please. Oh, I should mention there one last point on that slide. The system is described as being a system for data analysis and graphics, and Bill Cleveland had a lot of influence on that. And this became important. I'll get back to why it became important, but the idea of having the ability to create this graphics was very central to S. Next slide. Oh, so what set it apart? Well, it had these self-describing data structures, which could include recursive structures. So if you remember, SPSS essentially had a data set, a table, and you brought table, maybe one or more tables in, and then you had a table written out. And S allowed for richer data structures. The code was expressed as functions and function calls. So again, you can do this chaining and the interaction was through a read-eval print loop or the inclusion of program files. So you could do the sort of, bring in this package. It wasn't called a package early on, but You could also just sit there and type at it and get answers and say, oh, what happens if I do this? What happens if I do that? So this was where the extensibility came in. Also, the code was a first-class object, so functions could generate other functions, or they could generate expressions. And one of the things about it, when you start on a project like this, if you're going to do it with a huge number of different kinds of different kinds of data storage, it becomes a exponentially complex question, because it's, you have to handle all of these different branches in there. And one of the genius points of it is that the internal data structures were relatively simple. They're all fixed length vectors and so forth. And the structure would be like talking about the metadata of a data set was achieved through this list of attributes. Next slide. And there was a peculiarity here, because at the time, AT&T, which ran Bell Labs, was a regulated monopoly. And they couldn't get into other markets. So they couldn't sell software. They couldn't sell the Unix operating system. They couldn't sell S. They couldn't sell. And they could share software for research purposes. And so there were a number of statistics departments that were designated as beta test sites. And for S, it just meant that John Chambers said, hey, you're on the list. And a couple of times a year, we would receive a tape with the software written on it, a couple of pages of instructions. This is what the directory structure is, and their best wishes. Don't contact us, just see if you can get it to work. Next slide. And so the people at the University of Washington, which was one of these beta test sites, they ended up creating a company called StatSci, and I actually have my mug here for my tea, is a StatSci mug. And they marketed a product called S+. One of their big contributions was to port it to Windows. And they also, at those days, every workstation that you could buy had a different version of Linux, and porting it was very difficult, very time consuming. And essentially this company, which started out named StatSci and then became part of Mathsoft, I think, and then did a reverse to, I can't remember. The link to the Wikipedia page is there, so you can check that. Data graphics was a strong selling point. S+ became popular because you can do the graphics in there. And there were actually ads from SAS at the time saying, we're introducing this new ultra powerful SAS graph. And so you don't have to take your data out of SAS and put it into S+ and make the plots and then take it. And it was important enough that it was noticed by SAS Institute. Next slide. So other early technology developments, well, this was also around the time that personal computers such as the Apple II or the IBM PC started to come on. Even the Apple Macintosh, when it was introduced, they still didn't have the power to compile and run the statistical software, but their potential was sufficient to cause SAS Institute to rewrite their software. The Macintosh was important because it was to create a language that was like S, that could run on certain versions of the Macintosh computers that were at the statistics computing laboratory at the University of Auckland that Ross and Robert started that. Next slide. Also, during this time, the Free Software Foundation was formed to promote free software, especially the Emacs editor and the GNU system. And they used licenses like the GPL. So, the Free Software Foundation and the GNU system are led by Richard Stallman, and anyone who's worked with Richard Stallman knows he's a very creative person. There's a lot that he's accomplished, and he's also not an easy person to work with. But his great achievement was seeing that you could use this licensing to prevent commercial capture. And they started off, they were trying to create the complete operating system. They bogged down on the kernel. And then this fellow named Linus Torvalds in 1991 said, oh yeah, I've been playing around with this, IBM compatible computer. And I got the kind of soft kernel going here. So anybody wants to try it. And eventually that became the Linux operating system. One of the things about this is that they were used for web servers, and there was an acronym at the time that you had a LAMP server, which meant that you were using the Linux operating system, the Apache web server, MySQL, or MariaDB as it's now known, for the data handling, and then one of the CGI language, which is PHP, Perl, or Python. So that's really where I first encountered Python. And in combination with version control systems, these servers allowed for the distributed development and dissemination of software. So those last two bullet points were synergistic. By having the ability to develop the open source software, they were able to produce Apache and Linux and et cetera. And then those were able to be disseminated. So next slide, please. And this produces a peculiar economics, because especially at universities, setting up a web server was horribly difficult. And the first copy of the software was expensive in people time to produce. But because of this ability to disseminate it, subsequent copies were essentially free. And in the spirit of, we're all in this together, support was often crowdsourced through email lists, wikis, etc. And next slide. So you were able to create these open source software projects. And now there's a gazillion of them. We have things like GitHub and so forth. But at that time, just being able to have a place where you could say, okay, here's rproject.org or r-project.org, and this is where you go to get the software. And these are the mailing lists, et cetera. So Rossi Haka and Robert Gentleman created a language, and if you're familiar with Ross's piquant sense of humor, it was described as being not unlike S, because there were still a lot of issues about could you copy the design of a language. Now, internally, it's very different from the way that S worked. It's more influenced by Scheme, which is a flavor of Lisp. It's very popular if you're at MIT. An internal difference relative to S was in memory allocation and garbage collection, and that became really important to do that. Next slide. So building the community, Martin Meckler made some early contributions. I mean, they made it available on an FTP server at University of Auckland, and Martin's very, very pro open source. And so he started working on it. And then he would send patches and corrections. And eventually he was doing that enough that they said, hey, we're going to give you access to the version control system for this. And then he convinced them to release the source code under the GNU public license. Other statisticians, especially those already using S, began to contribute. The mailing list, the CRAN, and RCore were all created in 1997. R version 1.0.0 was released on February 29th, 2000. The major milestone on getting to that was the implementation of S4 classes and methods with multiple dispatch. Next slide. This is important, and I think that we've seen this over this conference, that the goal of the S language, and then at times we would talk about the S language and R implementation. was to allow users to progress through stages of use. You use the REPL as a sophisticated calculator. You find that you're repeating some operations, so you script some things. Then you find, oh, maybe it would be better if I just had a function that did this. And then you get the functions and the data and the documentation, and you put it into a local package. And then you can publish a package for others to use. So this was a real watershed in being able to incorporate R into statistics research and practice. And the other repositories that became clearinghouses of research and methodology and examples, it was important to have quality control. It was important to try to assure consistency of results. And that's why, the services provided by CRAN are so important. There was also the introduction of literate programming through SWeave, and then later Knitter, and now Corto. By the way, if you haven't seen Corto, you can see the name up in the URL for these slides. Corto.org is where to look. It's the next generation of Knitter and R Markdown. Later, the notebooks were introduced. Jupyter, of course, is very valuable in the Python community and Jupyter Lab. Next slide. Where am I on time? What's my end date? Or I'll just keep talking and you can shut me down.
I think we have about 15 minutes.
Oh, wow. I'll slow down. No, there's lots of discussion going on, so I'll go through this quickly. There was a big contrast when we get to open source software and when you get to closed source software or commercial models. Most commercial software did not encourage the extension by users. They might have some, you can contribute something here and it'll go onto this web server, but that's it. And if you want to contrast what was happening in the open source world and what was happening in the closed source world, Eric Raymond has an old book. It's called The Cathedral and the Bazaar. And really all you have to know is what's the title, because the closed source software is the cathedral. The high priests determine what you can do, when you can do it. And, they don't want you to get a medium, you don't get a medium. And all of the communication is down. Here it is. And if you look also at GUIs, GUIs are great. But I mentioned Brian Kernighan, and he is also famous for coining the phrase about when you go from text processing, Markdown or something like that, LaTeX, to a word processing. The word processing was often, early on, it was called what you see is what you get. It came from comedian Flip Wilson, who was on Rowan and Martin's Laugh-In. And Kernighan responded, yes, but it's also true that what you see is all you get. So that's the thing that really changed. The cathedral decided what you could get, and that was it. The bazaar, on the other hand, so that's the GUI part. Next slide. The bazaar. Oh, I'm sorry. I didn't know what the next slide was. Commercial support. Here I have to mention another big player. They're now known as Posit.co. We've heard many people talk about R-Shiny. Shiny actually comes out of Posit.co. The RStudio IDE comes out of Posit.co. The Corto document preparation system and the Tidyverse family of R projects all come out of Posit.co. It's a very interesting company because it is incorporated as a public benefit corporation, which means that they can take into consideration the impact on the community and not just sort of increasing shareholder value. So to many users, Posit.co is more central to R than is R core. More people would recognize Hadley Wickham and many of the people at Posit.co then would recognize most of the members of our core. But it is a separate entity, and they're absolutely wonderful. They've been doing such fabulous contributions to the whole community. Next slide. So where are we now? Well, we have powerful open source tools. I haven't talked about Python, but Python came out of this scripting and developed into a much more sophisticated language using classical object-oriented classes, and methods were parts of the classes and so forth. And it was able to work quickly, spin up quickly. So it's often used for utilities. It's fast to code, and it has the ability to call on compiled code as well. So, when you get around to machine learning, the initial implementation of Torch was in Lua, but then there weren't enough people who knew Lua, and so they went to having Python as the interface language and having C and C++ code sitting behind it. Julia has a smaller but dedicated following. I'm a Julianite. And each language is supported by thousands of packages. Now, I don't know that much about the Python package index.org. So I don't know what 500,000 constitutes there. I do know what a CRAN package looks like. So there's about 20,000 of them on CRAN. There's about 7,500 packages registered on the Julia registry. And amazingly enough, even Microsoft supports open source, and the biggest contribution there is github.com. They are tremendously generous by providing that facility. They also use VS, they also made VS Code, and many of these languages can interface quite nicely with VS Code. If you would have told me in the 1990s that I was going to spend most of my days in the 2020s working within two Microsoft systems, I would have told you you're crazy. So that just shows how much things and the attitudes towards open source software have changed. And they provide incredible opportunities, but there's so much to learn and remember. Next slide. So each language can be used, as I've said, in a REPL, through scripts. Jupyter, the name Jupyter actually comes from Julia, Python, and R, plus a couple of other letters. In document creation systems like Corto, again, if you're experienced with R Studio or you're experienced with R Markdown, with Knitr, you should definitely take a look at Corto. And it can be used in conjunction with version control systems like Git and internet repositories like GitHub and GitLab. Next slide. And they were really the key. The open source and the REPL were the key to be able to do this gradual development. And I think any person who's on this conference who's working with R or working with Python has had this experience that you're using the code and then you're extending the code and you're extending it a bit more. Again, this wasn't always a slam dunk. Open source was considered kind of iffy in the 1990s, and our efforts were dismissed as freeware or as the student edition of S+. It's that peculiar system, economic system, where you can actually get greater value out of the open source or the free software than you can from commercial software. And that seems very, very contradictory. Eric Raymond contrasted these again. I mentioned the title, The Cathedral and the Bazaar. Next slide. So the Bazaar is accessible, but it's confusing. It's wonderful to have these several different languages and systems with which to do data science. Within a team, you might be using multiple languages, but in any case, it's good to have exposure to more than one way to do an analysis, but few people are going to have the time or capacity to learn all of these different languages effectively. And so it's a matter of balancing the time to learn the tools versus the time spent using the tools. Next slide. And here's my conclusions. So I talked about the general trends in open source software, some of the support mechanisms that had developed as we've gone along, how the S language came about in the 1980s, some of the characteristics of the S language that made it particularly effective. Then R came along and provided a widespread access to this. Many people have contributed at many levels, and I think that all of those involved, I feel proud of the result because it's been an amazing journey. Thank you.
Thank you, Doug. That was great. We probably have time to take a couple questions before we conclude the conference. So I encourage everyone who has a question to use the Q&A functionality. We do have one that came in. So this one relates to the dozens of commercial SQL packages environments, Statistica, but the big names like SAS, SPSS, and Stata have survived, with only Stata being or allowing for this semi-open source development where you can have modules and contribute that through those repositories. How do you see that developing in the future and the future of that community or open source packages built for commercial software?
I really can't answer that because I think I've never used Stata. And the last time that I used SAS was in the previous millennium, at least. So I don't really know how things develop in those communities. It's a very delicate balancing act for a company who's trying to sell the software to then say, okay, well, we're going to provide access, because then there's some obligation on their part to vet the ones that they've produced. I mean, they're selling you this product, and if they're providing these user contributed packages, they might have greater legal exposure as a result of that. And, you know, it's not as prevalent today, but there were a lot of issues about the legality of open source software and what kinds of guarantees or suitability were in there. And that's why the GPL and so on has all of these disclaimers at the beginning when you start up the software, because you know, you don't want to contribute and then somebody says, oh, well, no, I got the wrong answers and you're responsible. Of course, that isn't true for the commercial software either. If you read their license terms, they're not guaranteeing correct results. But for a while, SAS was very strong about saying, especially the pharmaceutical companies, oh, well, SAS is validated by the FDA. And, you know, that's, well, that was an interesting characteristic. But we actually had to produce a report.
That is true, and that still happens today. We have one more question here. This one refers to advice on how to transition from different programming paradigms. For example, from structured languages like Fortran, SAS, trying these new paradigms of functions. I imagine, for example, like multiple dispatch. What would be a good resource or a way to pick up these new paradigms?
Again, I'm not a good person to ask. I've been retired for better part of 10 years. And so I'm neither teaching people nor learning at an elementary level on these kinds of languages now. I mean, you always are learning, but it's different different kinds of focus on what I'm learning right now. So I guess I would go to a community that's more accessible to newcomers.
Great. I'll put one last question to end the session. And this one refers to, in your experience, you mentioned GUIs and REPL as being key features to the success of a project, especially for open source. From the developer side, what were key features, whether it's coordination through mailing lists to GitHub now, that make it easier for newcomers to join as developers in that community?
Oh, well, certainly something like Git. I mean, there's an irony here that R is the one open source language project that is not hosted on GitHub. The master R sources are in an RCS system. But it's that, you know, following the various lists, following the repositories on GitHub, etc., is definitely a way to get started on there. As you know, most of my development these days is in the Julia language, so I'm following those. I'm not reading too much of R help or R devel, and so I can't really give too much guidance on that again.
Great, thank you. So we're out of time. I'll pass it to the organizers who have a brief message before we conclude the session and the conference. Thank you.
Peter, would you mind sharing our closeout slide here? Thank you. Really, this is all about saying thank you. I want to thank everyone for their attendance today. Thank you, Dr. Bates, for your recollections of the history of open source and taking time to present to us. This event was put together by a small army of volunteers. So thank you to our planning committee. I hope if you got benefit from it, you'll take a chance to thank them if you see them in person or connect virtually and thank them. Thanks especially to Donna Lalonde and the American Statistical Association for supporting this conference by use of the Zoom platform. It is our intention to share recordings and slides from this event on the FCSM CSPOS website as we update that and share the recordings at our GASP FCSM YouTube channel. And I will mention for presenters who are in attendance, there will be an invitation to participate in a special issue of the Journal of Data Science. We thank June Yan and colleagues at the University of Connecticut for extending that opportunity and for considering this event worthy of commemorating in a special issue. So with that, I think, Donna, we can go ahead and end the recording. And I just want to reiterate my thanks to everyone in attendance today for making this a